Hi, I'll now teach you about this concept of angular distance turnaround right here in the context of a specific example. So what I'll do is I'll use this Einstein de Sitter model. So I'll have you have this diagonal metric right here where on the x-axis and y parts we have t to the 4/3, and then on the tt part we have -1. Okay, now we'll use this in this metric right here, this curve, r equals 3t to the 1/3 minus b. B is going to be some constant. Uh, 0 on the y, and t for the time part. These are x, y, t coordinates. Okay, so now here I've drawn the coordinate system, and I've shown one example of these, of this curve r, which is a light like geodesic. That's that one that I had up here, this one right there. Okay, so there you have it. Basically, that's the form that it has. If you this thing is rotationally symmetric about any vertical axis, so if you rotate it around that same geodesic, what you get will still be a geodesic, rotation around the t-axis, let's say. And so that's the way of that. And then we're going to consider the following. This angular distance turnaround is basically this. There's an observer right here, right at this point where this curve touches right there, where it touches the t-axis. There's an observer there, and then this geodesic that you see right here is basically the light ray, the history actually of a photon that gets to him, right? But the thing is that this photon could have gotten to him from this point along that curve, or further down, at different values of t. So if you slice this, with planes parallel to the xy plane, you'll see, you could have had, any from any one of those spots, the signal could have had been sent to him. And now, the story about this is this: that let's say at this time right here, where this circle, that's parallel to the xy plane that I've drawn right there, is, if there's like a little piece of something right here a little something of a certain finite size, right? Then from either end of the thing he'll get a light signal. So it could be something like this picture down here. You see how there's these 2 points on that circle, and there's two light signals that reach the guy right there, okay, from those spots. So then, basically what we're going to do is this: we're going to be looking out at different times, and seeing how the angular size of these things change. Now it turns out, by the nature of this thing, these geodesics, like this one here, etc., they're contained in planes, basically. For example, the first one up here, that's contained, in the xt plane, and then these right here are right here are contained in some plane or other. So in any case, um, let me see. What? Well, not some plane or other. I mean, they're planes that both contain, the t-axis. But okay, so what we're gonna do is this. If you notice this down here, that little angle I drew down there, that's where those two planes that contain those two curves that are going up like two strings coming down from a tent or something. Okay, on that plane parallel to the xy plane, that angle that I drew there, that's actually going to also be the angle that this observer that's sitting right here will see those signals, those light signals coming in at. Okay, that you can prove, through a number of ways. Okay, right now I won't go into it, but basically, right here you would put a plane right at this point, and then you take the projection of the tangent vectors to those two curves onto that plane, and you can prove to yourself that the angle they make will be exactly this angle that you see down here in this thing. Okay, now this geometry is such that if I take a circle of this type that I've drawn here, like this, or here, take a circle of that type, just a circle in a plane parallel to a xy plane. Okay, such a circle will have exactly the same, or basically any curve in such planes will have the length will be the same thing as the Euclidean length, but multiplied by a factor, depending on at what height of t they are, at a factor of t to the 2/3. Okay, so now we're going to bring everything together now. Remember that whenever you have a circle, a Euclidean circle like this with a radian a measured angle, then what happens is that, if you take the radius times this theta, and you multiply them, what you're going to get is this length of this arc right here, S, a little arc right there. Okay, so I have the formula right here. That's what appears there. Okay, and then I did some algebra, just flipped it so that I can get what theta is, because that's what we're going to care about. What we're going to do is we're going to look at different t's, at different values of t's, and we're going to check what's the visual angle for the signal coming from that time period. Which, by the way, another way of looking at those times t's, there also corresponds to distances along the x-axis, or basically away from the t-axis, and they also, if you look at it another way, you could translate that into relating redshifts, because each one of those distances in the x direction corresponds to a different redshift. Okay, so this you would be basically the observer. That would be you right there, looking out at distant galaxies at different, values of t, which is basically at different epochs or whatever you want to call it. Okay, so that's how it is, and the whole thing is basically what we're going to notice is that for a fixed size object that you look at this way. So, for example, that fixed size object could be this little arc of a circle right there, from the in between the two tips of those two light signals. Okay, you'll take a fixed sized object of size k, of native length k. So in other words, if you're near the object, that's the length that you would measure. And then what you're going to do is you're going to look at light coming from the particular epoch that you're considering from that object, and you're going to see what angular size you see this at. Okay, so here we go. So you fix a length k, then what did I say right here? The length of an arc at time t is just the weighted by that t to the 2/3 from the metric times whatever s the Euclidean length of that thing is. But in our case, we wanted the thing to have length k. So what we're gonna do is basically that you're going to find some arc such a multiply by t to the 2/3, because we're looking at time t. It will have length k. Then when you solve this algebraically, all you'll get is this, basically, that you'll find out what that s, in other words, what the Euclidean length of that circle arc right there has to be a wait, let me see what, yeah. So basically it's going to be k divided by t to the 2/3. Okay, so now your angle theta then is going to be that s, which is k at t to the 2/3, divided by r. That's what we saw in this formula right here. So then you see it right here that I solved that out, and then it turns out that distance, the distance out to this thing right here, is actually, notice, the x coordinate of this right here, okay, of that light like geodesic, and therefore that's why we have here the absolute value of 3t to the 1/3 minus b. Okay, so now putting it all together, that's the formula for theta. Theta is equal to this, k over t to the 2/3, 3t to the 1/3 minus b. By the way, that k is not the usual a curvature in Robertson Walker metrics or nothing like that. That k is just the native size of a particular object in the sky. Like if you were near that planet or whatever, what was the actual length of it? Okay, so now when you do that and you graph this function theta as a function of t, you get this. Okay, when you plug this into any graphing utility, you're going to get this graph. But remember that here, this is a Big Bang model, and there's no values of t less than 0. So in others, this is the t-axis, this is the theta axis, and these values are not going to be used, the ones on the negative side. And it turns out that between when the light signal is sent anywhere along here to when you get it right here, right? That's basically this time right here. So this right here is the time at which you get it. So you notice that just between those two times, the part of the graph you're going to need is this thing that looks like a U. And there you notice something. If you start with objects very, very close to you, of course, if you put something tiny next to your eye, it's going to look humongous. That's why, say something of finite size, as you bring it to zero distance from your eye, the angular size is going to be infinity. But then, as things get further, as you normally expect, they get smaller and smaller and smaller. But somewhere after a certain time, some time down here, getting close to the Big Bang, you notice that again, the angular size actually starts to grow. And actually, from what we see here, it grows infinitely. So objects again become humongous as you get really, really, really close to the Big Bang. In fact, they go to infinity. So this is this phenomenon seen right here in the Einstein de Sitter model of what is called an angular distance turnaround. So galaxies, further back in the past, after a certain point, will start to become bigger again, and that's basically it.